Okay, so we're gonna go ahead and start. So first things first, my name is Zane. How's it going, everyone? And this is part of the Google Developer Student Club. We're hosting a foundation exam review. So just a quick preview. And by the way, this is an attendance form. So you guys can scan that just to log yourself in. And so the Google Developer Student Club is part of a larger organization, Google Developers. So we're just kind of like a subset of them. And some of the things that we try to do is help students bridge the gap between theory and practice. So, we do a lot of projects, we do a lot of workshops like we're doing right now, to help you guys, understand some of the theory behind the foundation exam in this case, and then practice it with practice questions. And we have a lot of different things that we do. So, peer-to-peer learning. Okay, actually, I don't think you guys can see that. Okay, well, the text is kind of blurred for some, or it's kind of like off-white. But yeah, you can meet people, make teams, build projects, and play with different technologies. And if you do want to join GDSC, it's pretty easy. You just kind of have to scan this right here and go to this URL. So again, this is attendance form, or a form to know how to join the club. And yeah, that's pretty much about it. As for the FE review sessions this week, we're going to be doing recursive code, binary trees, tries, and hash tables. And over the next few weeks, we're going to cover all the fun stuff. So I know week 4, everyone's so excited for week 4. It's probably what people have the most trouble with. But yeah, we're going to do a lot of recursion stuff today and something on the lighter side, hash tables. So yeah, that's pretty much it for the slides. So let's just hop straight into the questions. So we're going to start off with recursive coding. So first things first, by the way, I'm going to link this here in case you guys want to practice along on your own. I sent the link in the chat, and yeah, there is a recording for week 1. So it's, I believe, in event resources in the Discord, so you can go there. So we're going to talk about recursion first of all. So recursive coding, let's say, for example, you have a linked list. So we've already covered those in the previous section or session. So let's say we have a linked list, right? And we have numbers in this linked list. So let's say 1, 2, 3, and 4. So how can you go through it regularly? When I say regularly, typically we start off learning how to do things iteratively, and then we go into recursion. So if you wanted to print this linked list, let's say in the same order that you have access to, so this would be your head, then you can go, okay, you can go here to this node, you print 1. So we printed 1, then we go to this node, we print 2, 3, print 3, 4, print 4, and then we get null, and then we're done, right? Now, what if I were to ask you to print out this list in reverse? And this is kind of where you can apply recursion, or you can do this iteratively, but you kind of have to reverse the list, or maybe store these values in some sort of way with a stack or something. But let's say we wanted to use only recursion to do that. So ideally, the way that we would end up doing that is we would end up going all the way from this point to the end. We hit this null case, and with recursion, there's different ways to go about actually, solving a problem. You might want to print first, or you might want to print afterwards in this case. So if you print first before you end up recursing, and recursing just kind of means, the way I like to think about it is there's different levels to the recursion. So when we start off, we make the initial call. So let's just put a star here. So this is the initial call, right? So this is kind of our first range or level of what I kind of call depth, right? So we're at the very top, and then as we keep progressing, so we go from this node, and now we go here, and we say, okay, we have another node. Now we're at this level. We're going to keep going, right? So we're doing recursive calls first. Now we're going further and further along. We make a recursive call here, and this is what's called the base case. So the base case is really when you want to stop, because otherwise you might run into issues, or you might hit like a time limit exceeded because it's kind of recursing too much and there's not really an end to it. In this case, since you kind of have to access different things inside of a node, so for example, a next pointer to go here, when you end up hitting null, you want this base case because you're not going to have a next to go to. Null is just kind of terminal. It's like, okay, this is the end, so you can't keep going from here. So you need a base case to say, okay, this is the point where I'm going to stop. Now, once we're done with this level, we end up coming back. Now we're back at 4. And this is where we can end up printing. So after we've done the recursive calls, we can end up on the way down, meaning right after we come from the recursive call, we can print. So now we're going to end up printing 4. So that's tied to this recursive call. Now we're done. Now we come back up to the previous level. This is where we can print out 3. We're done. And so on. So now we're going to print 2. We're done here. And now we come back to the original call. We print 1. And then at this point, once the initial call ends up returning out back to wherever it was called, now we're done with the whole recursive procedure. And this is just a simple example on linked list, just trying to print it in reverse, doing it recursively. You know, there's binary trees, there's tries, and we're going to touch into that. But just as a quick little intro to recursion and a simple problem on how to use it, or that you might want to use it. So that's just a small intro to that. So we're just going to hop into some of the recursive coding questions. So let's start off. Okay, so I'm going to give you guys just 1 minute to kind of think about this problem, and then we can just kind of hop into it. I don't want to do the usual 2 minutes, so that then we can get a lot more questions in. Okay, so let's go into this question. So write an efficient recursive solution. So these are 2 things we should take note of: efficient and recursive. They made it bold for us, so you know it's important. That takes in a sorted array of numbers, 2 integers low and high, representing the indexes into the array, and another integer value, and returns the index in the array where value is found in the array between low and high, inclusive. If the value is not found between the indexes low and high, inclusive, then the function should return -1. Okay, so just so we can do a little survey, what type of approach do you guys think we're going to use? Like what algorithm, or how should we end up doing this? Yeah, exactly. So Justin got it. So we're going to use binary search, and we can tell it's going to be binary search because it says efficient. We're searching for something, and it's a sorted array. So it can be a sorted decreasing, increasing, or however else. So let's just draw out how this would kind of look. So we have 2 indexes. Let's say we're given 5, 8, 9, and 12. Right? And they said that they'll give us any type of, okay, let's do another number, and 15. Okay, there we go. So they'll give us any values, so low and high, that are indexes. So we have indexes of 0, 1, 2, 3, 4, and 5. So let's say they give us a low and high initially of 0 and 5, right? So we start off with 0 and 5. So with binary search, at any given point, we're going to take the middle of the values, so the middle of the range, and then we're going to decide, okay, for example, is the value we're looking for. Is it this value? If it's not this value, is the value we're looking for on the left side of this value that we're at, or is it on the right side? And in that case, we're going to want to end up only focusing on the, let's say, for example, it's on the left side. We're only going to want to focus on this new range of values. So we're going to ignore this other half because we know for sure it's not going to be here, right? So let's say we were looking for 5. Then in that case, we would say, okay, we don't care about anything of this value where we're at or anything to the right of it, because we know 5 is less than 9. And since it's sorted, it's going to come before 9, meaning it comes to the left of 9. So now this is the area that we care about. So now our indexes go from 0 to 5. For example, I didn't necessarily do the midpoint, but actually, yeah. So 0 plus 5 divided by 2 gives us 2. This is our midpoint. And then we're going to end up checking this range. Now we have 0 and 1. And between these two, the formula for binary search, you find the midpoint. You just add these two values and divide by 2. So we have 1/2, and then this actually is just 0 because how C does its division. So now we have a midpoint of this right here. And in the case that we find a match, which we do have a match, our target is 5 and we found a 5, we end up returning 1. Let's say we were looking for, instead of 5, we were looking for a 3. We would end up seeing, okay, this value is not 3 and 3 is less than 5. So we're going to go to the left. So now our new area that we're looking at is over here. But the thing is, this takes us out of bounds, right? So we can't really go there, and there's really nothing else, in that area. So we're going to want to end up ultimately returning -1. It's the same case if we're looking for example, 16. We're going to end up being at this point, and then we're going to end up just going straight to the right. So we're going to look at everything here. There's nothing there. We just return -1. Or for example, if we were looking for 10, there's no 10 here, so it's also going to return -1. So that's kind of what we're doing. And with each recursive call, we're looking at a new sub range within the full range that we started off with. So that's the whole idea behind that. So to hop into the code, since we're doing this recursive, we're going to want to know whether or not we've what I call exhausted the search space. So in this case right here, where we ended up, so we had a low and then a high here, right? So whenever we want to go to the left, we would end up moving our high 1 position to the left of the mid, because this was our low, this was our mid, and this is our high over here. We end up moving our high here. And now at this point, we notice that our high and low, or our low and high, have crossed over. This is what I call exhausting the search space, because now once they've crossed over, you've made sure, okay, I've went through every possible thing that I could. Now that we've crossed over, there's nothing else to search. But at the start, you had a full window of all these values, but then it ended up going here. And now you've crossed it over, and now, okay, now there's nothing else to search for past this point. So at any given point, we want to check if our low is less than our high, because that's how it's going to start off. Less than or equal to our high, because they can be at the very same value, and that can be our answer. And we're going to want to calculate the midpoint. So we can just have a mid variable, and we can just calculate that with low plus high divided by 2. And that'll give us the middle index that we're looking for. After that, we have this value. So this is our target value. So let's say we're going to handle the case where it's to our left, then to our right, and then if it's the value where we currently are at. Just to make it, yeah, let's just do it like that. So if the middle value is greater than the value that we're looking for, then we know we're going to have to go to the left, because, okay, it's just the same case that if we were at 9 and we're looking for 5, we're going to want to go to the left. So what that's going to look like is going to go return search of numbers. Our low is going to stay the same, because now we're going to want to adjust our high, because now that we're moving our window to the left side of the array, the low is still going to stay where it was, but our high is what has to come down. So if we were at mid and we know mid is not the value, right? So if it's greater, that means it's the value we're looking for is less than what's at the mid. We're going to have to move our index one before the midpoint. So we're going to do mid minus one. And our value still stays the same because we're still searching for that same value. Now, in the other case, let's say our value is greater than the mid. That means it's on the right of the mid value that we're at. So if we're on the right, our new window, our high is going to stay the same because we don't know how far right we're going to end up going. However, our low is going to have to move one past the mid, like on the right of the mid. So I'll draw it out so you guys can see. I can get my explanation. But our low is going to move up, and our high is going to stay the same. And then in the case that the only other case, okay, we're not less than, we're not equal to, or we're not less than, it's not greater than, and then it has to be equal to where we are at. That's the only other case. So in this case, we're going to want to return one. This just means that, okay, we found, or actually not one, we're going to want to return the index. It asks us to return the index where we found the match. So this is the matching case. So we just return mid. Mid is exactly where that number is in the array. And at the very end, there's a few cases. It's like, okay, we didn't find it, or we end up crossing over. If we end up crossing over, in the else case, we just return -1. So we can either write an else here, return -1, or we can just have -1 here, and it just does the same thing. So we still like that. So yeah, just to go through it again. Right here, where we knew 5 was to the left of our, sorry. When you find your mid, are you looking at the actual values in the array or the indexes? No, so pretty much you're using the values in your array to kind of guide, okay, where am I going to go? Am I going to go towards the left or towards the right? And then whenever you find the match, you just want to return the index where you found it. So let's say I was looking for 5, I would just return 0. If I was looking for 13, I would return 4. So that's kind of where we're returning. So yeah, just to go back to what I was saying, when we were looking for 5 and we were at a mid of 9, our low still stays the same, but our high is what ends up going from this point where we started at. It moves all the way over here because now we don't care about anything over from this point to the right. So that's the whole idea of moving our indexes for low and high. And in the case that, let's say we were at 9 and we were searching for 12, we would end up moving our low from here to here. And then now we only care about this range from low to high. So that's the whole idea. Yeah. The indexes is just what you return. So let's check out the solution. Yeah, so they did it a little differently. So if low is greater than high, this is the crossover case I was mentioning. Low, just by the name of it, low must be, it can't be greater than high because then it's not really a low, is it? So then we've kind of crossed over, we exhausted everything we can search through, and we return -1. This is the same thing that I did here, just written a little differently. Then we check for our midpoint. In the case that value is greater than the midpoint, meaning we have to go to the right, that's what they did over here. Then we put our low at mid +1 and our high stays the same. In the other case where we're looking towards the left of the mid, we move our high down to mid -1. And in the case we found a match, we just return mid. So yeah, that's full points right there. So let's go on to the next question. Okay, this is Towers of Hanoi. This is probably one of the more complicated ones. I'm actually going to skip this one, not because I can't do it, but because you're going to have to understand like the whole Towers of Hanoi algorithm. And honestly, this doesn't really come up that much. So I wouldn't even worry about Towers of Hanoi. I know it came up on one of the previous exams and it's a pretty short solution, but we'll just end up skipping it. Okay, so let's give you guys a minute or two to think about this one. Okay, so it says write a recursive function that returns the product of the digits of the integer input parameter n. You may assume that n is non-negative. For example, product digits 2, 7, 4 should return 56 because 2 times 4, or sorry, 2 times 7 times 4 equals 56. So we just want to multiply each digit in the number. So let's think about how we can end up doing that with recursion. You can do this iterative, but that's not what they're asking for. So let's think about it. So you're given this number, 247. So this is your parameter. Let's just call it f, right? So you're given this number, and we're going to want to know how are we able to kind of isolate every single digit in this number until we've gone through all the digits in the number, right? So what that would look like is, okay, maybe we can pick just randomly. Let's just say we pick a 7. Then somehow we can isolate a 2. Somehow we can isolate a 4. And, we're multiplying all these together until we end up at 64. Now, the thing is, you can't just pick them randomly. You probably could, but it'll probably be, you probably need more parameters, or it'll be just more difficult. So let's think about how we can do this one by one in a way that it can be done recursively, because the thing with recursion is it's going to apply the same logic to every single call that you end up doing. So meaning you can't treat how you get 7 differently than how you get 2 generally. So for example, if we wanted to get, let's say I ask you, okay, what is the least significant digit of this number? So what that means, you can just think of it, okay, what's in the ones place? So in this case, we know that in the ones place we have a 4. So we just put a 4 to the side, right? How are we able to get that number? We can end up just doing the mod of the whole number by 10. Because remember, whenever you do mod, it'll give you a number. So let's say this is your n. Let's say this is your mod value, right? This is going to give you a result from 0 to m exclusive. So that just means that, okay, whatever we're going to get is going to be from 0 to 9. So it's not going to include m, so it's just going to include from 0 to 9. So this is going to give us, okay, how many times does 10 go into it? Is there a remainder? Yes, there is a remainder. So we have a remainder of 4, right? Now that we have this number, how exactly can we end up going to the next number? And the thing is, in C, whenever you do division, on integers, right? So whenever you do division between integers, it'll just end up cutting off values. So for example, if we do divided by 10, we know that this is going to be, and then let's just not do integer division. This is going to be, for example, 24.7. But when you do integer division, it just cuts this decimal off. So you're just left with flat 27, right? So now we're left with a 27. And now we've got the next digit that we're going to want to use. Okay, So now right here, we can end up applying the same recursive procedure. Remember, you're gonna want to apply it the same when you do recursion, because that's really what's gonna end up happening. So now we can end up just doing mod 10. We're gonna end up with a 7, and we can follow the same type of procedure. Okay, we end up with a 7, but we're gonna want to get to the next number. So now we have 27 divided by 10, which gives us, okay, let me just circle this out. Yeah. So this ends up giving us 2. Which, right, it's 2.7, then you cut it off, and then now you're left with the 2. Now at this point, you can end up dividing it one more time until you hit 0, or you can end up just returning this number. Because think about it, if you end up doing the same procedure again, you're gonna do mod 10, you're gonna just be left with this number itself. So now you're gonna be left with a 2. And if you try to do the same thing where you do, okay, 2 divided by 10 is equal to, like whatever it ends up returning, it'll be 0.2, right? But it just cuts it off. Now we're left with a 0. Now you might be thinking, okay, now that I have a 0 as my number, why don't I just return 0 so I can multiply all these numbers together? The problem comes with that is, okay, now you're gonna have 0 times whatever you got here. So you ended up getting a 2. So now you have 0 times 2, right? And what does this end up giving you? It ends up giving you a 0. Then you're going to return this up to this number, 7 times 0. You're going to be left with, again, a 0. You're going to return the 0 back up to this number, times 0. And now you're going to return out to the primary call, the primary function call, a 0, but that's not your actual answer, right? So for you to kind of deal with that, if you do end up, when you get to a single digit and you end up having a case, okay, if the number is 0 or whatever, you can end up just returning 1, because if you think about it, any number, any multiplication times 1 is the number itself. So if I were to change this, okay, if I have a 0, you're just going to return 1, right? So we're going to return 1. So now we do 1 times 2. It just gives us a 2. 2 times 4 is equal to 14. This 14 is going to return to this call. So I'm going to do times 14. And this ends up giving 56. This is our final answer. So if you end up going down to 0, you can end up just return 1 and multiply those out. Or you can just end up, when you get to a single digit, if this number that you're currently at is less than 10, you just return this number, because then you don't have to do this case right here. So that's just another way to think about it. And you make one less recursive call. It doesn't matter. You'll get full points either way, but just so you guys know about that. So let's solve the problem. So like I had mentioned, I'm going to do it the first way that I had shown you, once you get to 0. So in most cases, this is going to work. So if number equals 0, just return 1. Otherwise, we're going to want to say, okay, digit, you can just do number mod 10. And then you can do return the digit times whatever the recursion returns. And I kind of drew out the recursion and the different levels as I went through the explanation. So now we're going to do number divided by 10. And this is really our final answer. But there's only one case where this does not work, right? So can anyone think of a case where, this does not work? Just notice that it says n is non-negative. Well, no, not necessarily if it contains a 0 in the middle of the number. If it contains a 0 in the middle of the number, or really if it contains a 0 anywhere, it's just going to be straight up 0. So the only case where this type of algorithm fails is when the first call, like let's say we call it, right? So we're down in main, right? And we call it, if we call it on a 0, it's not going to work. And the reason that's not going to work is because we're going to have a number 0, and then we're going to return the product of the digits of a number that's just 0 as 1. But the product, actually, technically, you probably wouldn't even do that, because to multiply you need 2 numbers. But let's just say you were to pass a 0, right? Then this is going to fail. So really, all you kind of have to do, if you're trying to like deal with that case, you can just end up doing the other way that I had mentioned. If n is less than if it's less than 10, you just end up returning n. So like I had mentioned, if the number is just 0, we're just going to want to return 0. We don't want to return 1. This is the only case it would fail. But in the case that we had like 56, we'd end up getting 5 times 6 times 1. Or it would actually be 6 times 5 times 1. And that's 30. But that's good. Anything that's not 0 would have worked, but in that type of form that I wrote. And like I mentioned, you need 2 numbers to multiply. So, the chances you'll get that as a first number, unlikely, but just in case, Let's see. So, wait, if the number n is something like 109, wouldn't it return 1 when it simply goes to multiply? Let me see. Yeah, exactly. So it multiplies by 0. So wouldn't it return 1 when it goes to multiply? The thing is, 1 is the last number that's processed, right? So, for example, the way that we're doing it, we're doing mod, right? Mod does not work from the left side. It works from the right side first. So we're going to end up going, okay, 109. So this is going to give us a 9. We're going to multiply this by something, right? What are we going to multiply it by? We're going to multiply it by, and now we have 10, right? So now we're going to do 10. So let's just do, just write it like this. Right, so now we're going to do, so now we have f of 10, because we did 109 divided by 10. And here we're going to say, okay, what is the least significant number? We're going to have a 0. There's going to be a 0 times, and now we're going to divide 10 by 10. So now f of 1, right? And now we're going to keep on going. So f of 1, we're just going to end up returning 1 in this case. So now we're going to have 1, right? So f of 1 equals 1. We agree on that. So we can just substitute 1 right here. So now we have 0 times 1. What does that equal? That equals 0. And in this case, f of 10 is what should be right here. So we have f of 10. So we know that f of 10 is equal to 0. So this is going to be 0. And then 9 times 0 equals 0. So that means that the whole answer for 109 is just 0, because any number times 0, doesn't matter if you how many digits you got, it's just going to end up being 0. So that's the whole idea behind it. And that's why it does fail in the single digit case for 0. But yeah, that's about it. Yeah, you could have also written it like this. I would normally write this like this, but just to make it a little clearer, you can also do this as well. So yeah, same exact thing, same answer, same number of points. All right, so let's do one last question. Okay, this one should be fun. All right, I'll give you guys like 2 minutes and then we'll hop into it. Okay, so let's start off. All right, so write a recursive function that will give or return the binary equivalent of its input parameter, decimal number. You may assume that decimal number is between 0 and 1023 inclusive. Thus, the converted binary value will fit into an integer variable. So that's just saying there's no overflow. So for example, for 2 binary 46, you should return the integer 100,001 with 110. And 2 binary returns whatever this number is, 1 billion. Yeah, 1 billion. So first of all, let's just kind of think of how they're coming up with these numbers. So yeah, they're turning it into binary, but let's just think about it, right? So for those that were around for my previous FE session under Shep, what's the biggest number that can fit into 46 that is a power of 2? So it's going to be 32, right? So we're just going to draw out our number. So 32. Then actually, yeah, let's just do it this way. So we have 46, right? So we can fit in a 32. We subtract that out. I'm going to end up with a 14. So now we just have a 1 here. And then we want to see, okay, how can we fit in a 14? So let's just say this is 2 to the 5. We know that we're going to have 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1, and 2 to the 0, right? So where does 14 fall into here? So it falls into 2 to the 8, or sorry, 2 to the 3, which is equal to 8, 2 to the 2, and then 2 to the 1. And these two numbers are 0. So this right here is 32. This is 8. This is 4. And this is 2 right here. And all these together add up to 46. So this is how they end up getting this number. So this is the number that they ended up returning, right? Now, the thing is, they give us 46, and we have to do this recursively. We have to take this number and make it into this right here. So let's think of how we can end up doing that, right? And one thing to note is that when you end up having a bitwise number, we're kind of building it from the lowest possible power of 2 upwards. So for example, what I mean by that is this is actually 1, then this is 2, this is 4, 8, so on. So you wouldn't want to kind of flip it. So you wouldn't want to have 0, 1, 1, 1, 0, 1, because that's not the same number. This is a completely different number. So let's think about how we can end up doing that, right? So at any given point, we're going to want to see, is the number that we're currently at divisible by 2? So we know that 46 mod 2, this is true, right? So if it's divisible by 2, we're going to want to, actually, sorry, if this is equal to 1. And let's think about why we would want to do that, right? So at any given point, we can see where a bit is on. So let's say we end up passing in 46, which is actually this number. So under the hood, 46 looks like this in binary. So we can end up shifting to the right to see, okay, what is the next bit that we can end up using? So if we're right here and we end up shifting to the right, we're now going to say, okay, now let's look at this number that's right here, right? So now we're only looking at this number right here, and we can see whether or not the bit is on. So then we can build out this number 100,001, 110 by checking, okay, is this odd? Like, is this divisible by 2? If it's not, then we know that it's going to be on, because whenever a number ends with a 1 bit on, that means that it's odd. So for example, if I give you 7, 7 is this 111. This right here is equal to 7. We know that it's odd because we know that a bit is on because we have this value all the way to the right on. And we can end up using the same logic to end up building this number out, right? So what's going to end up happening, instead of just going, okay, we're going to look at this number first and then the next number, we're going to end up actually starting all the way at the very end. So what's that look like? We're going to end up doing recursion first, and then we're going to end up building the number in reverse. So we're going to break the number down. So let's just think of how that's going to look. So now we're going to look at this number, and we're going to end up looking at this number, this number, this number, and then we end up with this one right here. So how can we go from having this number right here down to actually returning this number, which is what 46 represents? So this initially is 46. And then we end up just shifting it all the way to the right until we're left with a single bit, right? And this is either going to be 0, it might be 0, or it could be 1. So it's always going to be less than or equal to 1. So what we can end up doing is in each recursive call, so in this case, it's a base case, we only have 1 bit on, we're just going to return 1, right? So we come back up to this level. So now we're going to return 1. So let's just put this 1 over here. And we can end up checking, okay, is this lowest bit right here, is this one also odd? Meaning, is this bit on? If the number is odd, that bit is on. In the case that it's not, what's going to happen is we're going to know that we're going to want to fill that number in as a 0. But we're going to want to build it based off of what the previous number we ended up returning was. So we ended up returning a 1. So we're going to want to do times 10, because this is going to allow us to have an extra space where we can put in whether or not we found a digit on or not. Or sorry, a number with the lowest bit on or not. So now we do times 10, right? So now we have 10. But we notice, okay, this is a 0. So what are we going to do? We're going to add on a 0. We're not going to add on a 1, right? So we have a total of a 10. Then we're going to end up returning 10 back up here. So now we have 10. And we're going to see, okay, what is this number right here? Okay, this number is a 1. So now we're going to end up doing, and remember, we're doing times 10 every single time. So we're going to do 10 times 10 plus 1, because this bit right here was on. So now we're going to end up with 10 times 10 is 100. 100 plus 1 is 101. We're going to end up returning 101 back up here. And I hope you guys start seeing kind of how I'm thinking about this problem. Now we're going to have times 10 times what we ended up getting here, so times 101. And what are we going to add to it? This bit is on, so we're going to add on a 1. This is going to end up returning to us this number right here, which is going to be equal to 1011 1. Now we're going to end up doing the same things, times 10. And we have to see, okay, is this bit on? This bit right here is, it's still not, it's on. So we're just going to end up adding 1. And then right here is where we're going to end up pretty much returning the final number. So now we're going to end up having this right here. Is this bit on? No, it's not. And we're going to end up like doing times 10 again. And then we're going to end up with our answer. So this is kind of the whole idea behind this problem. You're just going to be returning based on whatever this value is and multiplying it by 10, adding 1 or adding 0 based on whatever the value is. Would the second to last call be 10, 10? Oh, yeah, my bad. I ended up skipping one. I ended up skipping. So yeah, there we go. And yeah, I think that would make this one this. And then when we end up doing it in this call, we would end up having 10 times. Yeah, that's a good catch. Thank you. Plus 0. Yeah, and then this is going to be our final answer. There we go. So it's a match. So we ended up taking the bit representation and turning it into an actual integer. So how would we actually end up coding that? I know that might have been kind of confusing, but I hope you guys kind of see the logic. And you can tell that you're doing times 10 just by thinking of, okay, what are the numbers in a bitwise, so in a bit representation of a number. So we're only going to have ones and zeros. So the way we can kind of add space for another one or another zero is by doing times 10. That'll give us another place where we can end up adding a value to our array. So that's the whole idea. So if decimal number is less than, we had said, okay, bit numbers are only going to have zeros and ones, right? So if it's less than or equal to 1, just return whatever it is, right? Now, in the other cases where, let's say we kind of want to see, okay, are we, like if we're going to keep on recursing, do we have an odd number? Meaning, is this bit that I'm currently at, is it on or is it off? So we can end up doing int, let's just have is odd, and we can do decimal number mod 2 equals 1. So we can check, okay, the number is on. We can either say is odd or is the bit on. Let's just do is bit on. And at the end of this, what we're going to want to return is, remember, we're doing times 10 based on what we ended up getting from before. So then we can see or say, okay, this bit that we're currently at in this call is on or not. So we're going to do times 10 of whatever we got from the recursion. So that's going to be decimal number. And we're dividing by 2 because we're kind of cutting bits off, just like I had done in this example. We ended up starting here, we came down here, and we ended up recursing back up. So we're going to want to divide by 2 to kind of shift. Okay, now we're here, now we're here, now we're here, now we're here. So there's 2 ways you can do it. You can either do it like this, divided by 2, or you can just use the shift operator. It doesn't matter which way you do it. Both of them divide by 2. Let's just go with this one. And at the very end, you're going to want to add whether or not the bit is on, because that's going to say, okay, this is a 1 or this is a 0. So we just add on is bit on. And that's really all you have to do for this problem. Another way that you can also check if the bit is on, this one is another way to go about it. We can actually do decimal number and 1. So for those that know their bitwise pretty well, this is another way to do it, but you don't have to do it. That's that way you can check the number has the lowest bit on if it's odd currently. So let's just check out the solution. Yeah, so they ended up doing decimal number is less than 2. So that's the same thing as this. And return 10 times the recursive call. And this is if the bit is on. So it'll end up just returning a 1 or a 2. It doesn't really matter. And I also do this equals 1. That if it is on, then it'll just end up, also returning 1. If it's not on, it'll just return 0. It'll give you the same answer either way. So you can remove it, you can keep it there, it doesn't matter. Okay, so that was it for recursive coding. Does anyone have any questions? Oh, okay. So now we're gonna hop into how to traverse tree recursive. Yeah, we're gonna go into those. So I'm gonna go to binary trees. Okay, this is probably the worst one you can start with. Okay, we're not gonna do this one right now. All right, so let's segue into binary trees. So let's just draw out a little tree right here. This is not a binary search tree, by the way. I'm just making it random. Okay. So the way you can traverse the binary tree, there's really 3 ways you can end up doing it. So the first that you probably learned is pre-order. Then we have in order. And then we have post order. And I'll show you guys how to traverse each of them real quick. So why would you want to use a binary tree? It's just another way to represent data. And depending on how you organize it, you can actually use it to make certain things, like, for example, searching, if you use a binary search tree, to make it more efficient than, just going through an array and searching for a value if it's not sorted. So yeah, it's just a way to organize data. And in this case, this is not a binary search tree. It's not organized in any particular way. I just kind of randomly made it. So let's do pre-order. So pre-order is just kind of how it sounds. So we're going to want to, for example, do whatever it is we're going to do at this current node first. So most cases when you have to do a pre-order, like the easiest case is just print, right? So we print, then we recurse left. Let's do recurse left, and then we end up recursing right. Right. Okay, so I'm going to end up using the same concept of levels that I've been using. So our first initial call is going to be on the root. So this right here is going to be the root of the actual tree. So what are we going to do? We're going to end up printing first. So let me just move this over. Okay, 5. So we end up printing 5. Now we're going to end up recursing to the left. So now we're going to be at the left child. And notice we have a left child. If we didn't, we would just end up returning out. That's typically the base case you use for a binary tree. So now right here, we're at the node. Now we're going to print. Now we're going to end up recursing left. We're going to notice, okay, there's nothing there. It's actually null. So we're not going to do anything. So now we're going to recurse to the right. We're going to see a 10 and print. Then now we're going to go to the left child. We're gonna it's gonna see a child there, a node there, print 6, try left, there's nothing, try right, there's nothing. Now this is where you end up seeing the actual recursion where you're like coming back up the tree. So this call is done. We've explored everything in this area. Then now we back up here and we've just recursed left. So now we have to recurse right. We notice there's nothing there, so we're done. So now that we've printed, we've recursed left, we recurse right. Now we're completely done here. So now we're done with this level. Now we come back up here. We went left, we printed, we went left, we went right. Now we're done with this level. We come back up here, but we've only printed and recursed left on this node. We haven't recursed to the right. So that's where we're going to end up going to the right. So now we're going to print 20. And then we're going to go to the left. We have a left, print 50. Try the left, there's nothing. Try the right, there's nothing. So we've gone through all the things we were going to do. Now we're done with this call. We end up coming back up here, but we've only printed and gone left. Now we have to recurse to the right. So now we're here. We print 60. And then we end up trying to the left, trying to the right. There's nothing, so we're done. Now we are done with this call. We've gone through everything on this call here. We're done. And now we come back up to 5. We've printed, we've gone left, we've gone right. So now this call is done. And this is the full pre-order traversal for this tree. So now we can end up going back to the other ones. So just to write it back out. 6, 20, 50, 60. Okay. All right. So now in order. In order, typically you can kind of see the use of in order when you're on a binary search tree, but we haven't gone there yet. So in order, we really kind of move the steps around slightly. So we're just gonna end up printing in the middle, actually. There we go. We're gonna end up printing in the middle. So we're gonna recurse left, and we're gonna print, and then we're gonna recurse right. So we start off here. We're not gonna print. We're gonna go straight left. Left. Okay. Now we're here. We're at a node. Now we're gonna again try the left. We see there's nothing here. So we're done with that. Now we're back at this node, and this is where we're gonna end up printing it. So 10. Now we're gonna end up going to the right. So here's where we are. And then we're gonna end up going all the way to the left first. And here we're going to end up trying to go to the left. There's nothing. So now we end up printing 6. Then we try out the right. We see there's nothing there. And that's where we end up coming back out of this. So now we were here, but now we're actually going to be back at 10. So this is where we're going to print 10. Try out the right. There's nothing there. And we've done everything in this call. So now we're going to come back up. We've done everything in this call because we've printed, or we've gone left, we've printed, we've gone right. Now we come back up to 5 and we've only recursed left on 5. So this is where we print it, and now we go all the way to the right. Now we're going to land here. And from here is where we're going to see, okay, we have a left. Let's go. Now we're going to try a left on 50. There's nothing there. Then we end up just printing 50. Try the right. There's nothing there. We end up coming back up to 20. That's where we print 20. And then we go to the right to 60. Try the left. Come back up here. Print 60. And then we're done with this node right here. Now at this point, we end up just coming back up. We come back up. We're back at 5, and then we're completely done. So that's pretty much it for in order. And let me just write it back out again. So, okay. Now post order. This is typically the one that people have the most trouble with, but honestly, I think it's one of the easier ones. I think it's probably easier than in order, even though in order isn't that bad. But post order, the way I like to think about it is you're going to start at the first leaf from the left, and then you're going to go upwards or actually you're going to go leaf to leaf is the way that I like to think about it, right? So if you're at this point, right, you're going to end up doing it in this order right here. So it's post, so we're going to do this at the very end. So we go left, we go right, and then we end up printing. So notice how the recursion, you're going to end up just recursing as far as you can until you're done, and that's when you print. So if you think about it, at every end of a binary tree, like the terminal or the leaf nodes, right? They always end in a case where it's nothing to the left, nothing to the right. So this is really the first node you're going to want to print. So starting from the left side, you're going to want to start at the first leaf, and then you're going to want to hop to the next leaf that's in the parent subtree. So what does that mean? So if I'm right here, I'm going to end up recursing left. There's nothing to our left, so we're going to end up recursing right. Let me do this in a different color. I'm going here, recursing left, there's nothing there. Recurse right, recurse left. There's nothing to the left, nothing to the right. So we're going to print out 6 first. So this is the first node we're going to end up printing. Then we're going to see, okay, is there any other leaf to the other side of my parent? No, there's not. So then we're just going to go to our parent. So that's where we print out 10. Then we come back up here. We've already gone left, we've gone right. So now we just have to print. Now this is where you can just hop to the next leaf of your parent, right? So what I meant by that is, okay, now I'm right here. Let me go to my parent and see where's the next leaf, because really what's going to happen is you're actually going to make a jump after a couple recursive call. You're going to make a jump right here. But really, how does that end up happening? So we're done with 10. We end up going to 5. Then we end up recursing to the right. We recurse to the left. We try out the children of these two. There's nothing there. So then we print 50. So that's kind of how I was able to just say, okay, if we're at 10, the next one's going to be 50 right away, because that's really how it ends up working out. You just kind of jump to the next leaf that's attached to your parent from left to right. So now from this point, I'm going to look at my parent. Okay, what's the next leaf that I can reach closest to me? There we go, 60. Because then what happens here, you've gone left, gone right, printed. You come back up, then you're going to go back down to the right. Try the left, try the right, and now you're at 60. From here, you're going to end up coming back here to your parent. You've gone left on 20. You've gone right on 20. So you just print out 20. And you come back up to 5. You've gone left on 5, right on 5. So now you just end up printing 5. So that's kind of a trick to post order. So if I were to just kind of draw it out real quick, or just trace out how it looks. I would actually end up going like this. So just for the traversal itself, this is what the traversal actually looks like. In terms of the order you're going to print it in. Not how you're traversing the tree, but the order that you're going to print it in. 6, 10, 10, 50, 60, 25. You always end up at the last thing that you end up printing out is always going to be the root. So that's just how the recursive tree. So now after that intro, let's just start doing a couple of problems. So we're going to skip this one because this one's really, really long. So let's just try this one out. So I'm not going to give time to try it out. We're just going to hop straight into it. So it says write a recursive function that takes the root of a binary tree, possibly null, and returns the sum of all nodes that are left children in the tree. So see the example below. So it returns 15 plus 49, which is 64, since the only left children anywhere in the tree are 15 and 49. So we start off here. We end up checking, do we have a left child? If we do, add it in. So now we have 15. Let's say we end up going to 15. We end up going to 15. Then we see, okay, does it have a left? It doesn't have a left, so we're not adding anything in. Let's say we go to 10, doesn't have a left, we don't add anything. Then when we end up going to, let's say 22, we're going to see, okay, 22 has a left. Add that in. So now we add in 49. Let's say we go to 49. It has nothing to its left. Then we're going to go to 68. It has nothing to its left, and that's pretty much it. So we're going to end up adding 15 and 49. But let's just kind of think of how this is going to work when we end up drawing it out. So I believe the example was 15, 1, then you see it was 22. I think I ended up selecting the numbers wrong, but doesn't matter. Okay, let's say this was our tree right here, right? So we're going to start off right here at this node. And we're going to have to add somewhere. Okay, this is the sum that I have in this subtree. So this is currently the whole subtree of this node that we're at. It's literally just the whole tree. But as we end up traversing down the tree, we're going to have different things that we're going to add in based on where we are in the tree. So we're going to want to have some sort of variable to keep track of, what came from the left, what came from the right. So we would end up having, let's say, a sum variable. Sum is going to start off at 0. But we're going to see, okay, do we have a left? If we have a left, let's add the value of that in. So we can end up changing the sum variable to 15, right? So the sum in this node right here is 15. But then we're going to go left, right? It's going to start off at 0. We're going to see, okay, what's to our left? There's nothing. Okay, so sum is just going to stay at 0. Now we go to our right. Sum is going to start at 0 in this call. There's nothing here. Okay, we're done. We're just going to end up checking here. Okay, there's nothing to go to. So we're going to return whatever the sum was back up. So we ended up having a sum on the left side of nothing because there's no child there. However, in the case of the right, we ended up having a sum of 0. So now we can just add these sums together. And now we just have 0. So this whole subtree, there's 0 left children. So that kind of falls in line with the number that we have, right? Then we can end up returning sum from this node right here back up to the recursive call of this node. And we're going to end up adding whatever the sum was, right? So we ended up getting a 0 from this whole subtree because there's no left children. So now we have 15 plus 0. It's still 15. Now we're going to end up recursing down to this node. Sum of 0. However, we're going to see, okay, we have a left child. Let's add whatever the value is. So it's 49. Then let's end up going to this node, right? There's nothing to its left. And also, yeah, sum does start at 0. So we end up just returning 0 back up. So we have 49, which used to be 0. Now we're going to add whatever we got from the left subtree, which was nothing. It's still 49. And then we end up going to the right subtree. Same case, there's nothing, sum is 0. So we're going to end up returning 0 back up. So 49 plus 0 again is just 49. And we're going to return this back up to our parent. So the recursive call that called us. So remember, we had gotten 15 when we were at this node and we saw, okay, we have a 15 to our left, add that in. So now we're going to add in whatever we got from the right subtree, which was 49, to this sum. And this is where we have 64. And that's what we're going to end up returning back up to, wherever we call the function. So this is kind of how it ends up working. We have a sum in every single recursive call that starts at 0. And based on whether or not we have a left child, we add that in. Otherwise, it just stays 0. And we just kind of sum those up recursively until we get the answer for the full tree. And that way we know, okay, across the whole tree, this is the sum of all the left children that we have. And it makes sense because whenever we didn't have a left child, like right here, it's just 0 overall. So okay, that's my horrible desktop on my desktop computer. Okay, so let me go here. My laptop is not as messy. I just don't use this as much. Okay, so we're gonna end up having our first base case. Whenever we recurse somewhere and it's null, we don't want to go there. There's nothing to do there, so we can just return 0. That way we don't segfault. Then now what we can end up doing is having our sum variable. We have sum of 0. Right? And in the case that we have a child to our left, so if root left does not equal null, that's how we know there's something there. We can end up doing sum plus equals root left, and then whatever the value is, so data. So now we just added in to this recursive call, whatever the value of our left child is. And now right here, this is where we're just going to want to recurse further from where we are. Because right now in the very first call, we're just right here. We added 15 to the sum of this value of this recursive call. So sum right here is 15. We're going to go throughout the rest of the tree. So what's that going to look like? We're going to want to take whatever the current sum where we're at right now, which is 15, right? And when we're right here, we don't know what this subtree looks like without going. We also don't know what this subtree looks like without going to it. So we're going to want to recurse through all the subtrees we have. And we can just do that by add all left children left plus add all left children of the right. So this is really what the answer is. So if we want to just kind of break it down a little bit more, we can say left children in left subtree, right? So just so you guys kind of have a better idea of what these recursive calls mean. And we can just kind of use the same name. So left children in the right subtree from the node that we're at right now. Right? So this is really what's going on. This is the way you can actually think about it. And we can use the same variables to add. It's the same thing. We can think of sum instead of just sum as like value of left child. So that's another way you can kind of, use variable names instead of just looking at recursive calls and not knowing. I'm just doing this so you guys can visualize it. Okay, so let's check it out. So if root equals null, return 0. Sum starts at 0. If it doesn't equal null, we're going to add in the sum variable plus equals, okay? Add in the left child, so we did that. Then we can end up adding the sum to whatever we get from our left. So all the left children we find in the left subtree and all the left children we find in the right subtree. And then this is our answer. So that's full points right there. All right, so let's hop into the next question. Okay, this one's kind of easy, but I mean, why not? Let's end up doing it. Okay, so let me just recreate it real quick. And this is where I'm gonna have a better example to show you guys what I mean with post order. Yeah, so feel free to try it out while I'm copying. Okay, so pre-order, in order, post order, and is it a valid binary search tree? Okay, so this is the tree that they gave us. So in terms of pre-order, let's do that one first. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I can do text in here. Oh wow, that's so small. Okay, never mind. So I'm just gonna write little slots here. Okay, there we go. All right, so for pre-order, remember, we're gonna start off at the root and just go, we're gonna print, so that's gonna be 68. Then we're gonna end up recursing to the left, so 23, go left, 34, go left, 25, go left, go right, come back up here to 34, and we're gonna go right to 81, go left, 12, left, right, then we come back up to 81, go right, there's nothing. We come back up to 34, we're done with this whole call, because we've gone left and right and printed. So we come back up to 23, we end up going to the right, you see 53. We're done after we go left and right. We end up recursing back to 23, we're done, 68, and then we go right. So we see 16 first, and we see 87, and then we go to 76, and that's it. So this is the pre-order. Okay. That's the pre-order of this one. You gotta be careful. All right, now in terms of the in order, there's a way to solve this question. But remember, there's another part to this. It says, is this a valid binary search tree? You can solve it with in order if you know what in order gives you in a binary search tree. So let's just go through it and see what we can end up coming up with. So in order, you go all the way left. So let's just start at 25. Then we go back up to our parent. So we came here. Now we go up here. We go to 34. We print that. Go right. Go all the way left. We see 12. We come back up to 81. Then we go right. There's nothing there. So we end up coming back up to 34. And now we're done with 34. So we come back up to 23. So we print 23. We go right. We go all the way left, but we have a null. So we just come back. We stay at 53 pretty much. We go to the right. There's nothing there. So that's where we end up finishing 53. We come back up to 23. Then we're at 68, and that's where we print because we've processed everything to the left. And then we print, and now we go right. So in this case, we're gonna get to this node. We're gonna go as far left as we can. It's only up to here. So we print 16. Then we go to the right to 87, but then we have to go all the way left. And then that's when we end up hitting 76. And then we print out 87. So what I was mentioning with in order, the way you can answer that other question is to see if the in order is in order. So is it in sorted order? Meaning, is there any case where a value is kind of out of place? So we know that 12 is the smallest. And so that means 12 should be here. So, it's not there. So that right then and there just tells you, okay, it's not in sorted order. Same thing with 16. And, there's a couple other places like 23, they're out of place. So that tells you right then and there if it's a binary search tree. Because if it was, it would end up being 12, 16, 23, 25, and so on. Now let's end up doing posts. This is my favorite one. Okay. All right, so with post order, like I mentioned, start at the first leaf all the way to the right, and then you go to the next leaf that's connected to your parent. So let's think about it like this. So we start off right here, right? So, okay, 25. That's the furthest leaf to our left. And if you don't have a left, like imagine this subtree was in here, you just start on the right. This is the same process. So we're at 25. Now let's jump to the next leaf of our parents. Now we go, okay, 12. Now we see, okay, there's nothing to our right from 12. So let's just print 81. Now we've gone through everything on the left and right of our parent. So now we print 34. Now at 34, is there a leaf or is there something to the right of my parent? Yeah, there is. So let's go there to the next leaf. So now we're at 53. We've gone left and right on our parent. So now we go to 23. And when I say like, okay, now we're going here, now we're going here, I'm really just meaning this is the next place we're going to print. Of course, this is not the order of the recursive call. You're going to start from all the way up here and go down, but just in terms of how we're printing, this is how it's going to end up happening in this order. So now we're at 23. What's the leftmost leaf connected to my parent 68? Okay, it's down here. Good. So now we go to 76. Now, is there anything to the right of our parent that has a leaf or whatever? No, there's nothing. So just go up here. We've gone left and then we've gone right. Or there's nothing to the right. Now, we've ended up going left here. We've ended up going to the right here. So now we go to 16 because we've done everything there. And then now we ended up going left on 68. We ended up going right on 68. So now we end up printing 68. And the way you can tell for the most part when you end up doing this, when you end up doing a post order, the first leaf from left to right on your tree is always the first value, and your root node is always the last value. So that's an easy way you can tell if you've done it right. Sure, you can mess up whatever's in here, but generally, if you end up doing these two parts right, then you're good. And yeah, so let's end up going to the solution. Let's see. Oh yeah, and is it a valid binary search tree? Since the in order wasn't in order, it's not one. Okay, so 68. Yep, this is correct. So 81, then 12, 53, then 16, 87, 56. Yeah, so in order from here to here to here, up here, and then down here and up here. So that's kind of how that worked. And post order. Let's see if what I said was true. So 25, 12, 81, 34, 53, 23. You go all the way over to 76, 87, 16, 68. So yeah, that's it. And it's not one. Not a bad binary search tree. So that's good. Okay, so we'll do one more of binary trees. And then we're gonna go on to another question. This one's actually gonna take a little long, so I remember this question, I do. So we'll go on to a different one. Okay, there we go. Let's do this one. So I'll give you guys a minute or two to go through it. Okay, so let's hop into this question. So this one's gonna be a little more complicated to trace, but it's still a good exercise to go through. So let's see what it's doing here. So we end up, we have a base case, that's good, we return null. Then we have some function, it recurses to the left, and it recurses to the right. So we know right now we're going post order. So we're doing post order. So what does that mean? We're going to start at the leaves, right? We're going to start at 15. And we're taking a temp of our left. We're setting our left to what our right is. And then we're setting our right to what our left used to be. So this is a classic case of a swap. So we're doing a swap. And we're doing a swap, if we think about it, at every node throughout the tree. So what would that look like if you're doing a swap at every point throughout a tree, right? So let's end up doing a quick example. So let's say I have 10, 5, and 6. Let's just do this one right here. So let's say I'm at this point, right? And we're going post order. So we're actually going to start down here. Now we're going to swap whatever the left and right are pointing to, right? So in this case, we're swapping null with null. So that doesn't actually do anything, right? So it doesn't actually do anything. And on this question, I'm actually going to draw it out like this. So we start off with things connected like this, but then we're going to end up actually switching things over and pointing them like this, right? Now we're done with this call. We end up coming back up here, but then we go to the next leaf, right? So now we're going to end up swapping the left and right because we end up having null and null here, right? So we can just end up, we know that it's going to be like this by default, but we end up swapping things. So left now points here, right now points here. Now it looks like nothing's changed so far, right? Now this is where you can actually see what's going to happen throughout the tree. So we ended up going left, we ended up going right. So now we're back up here. And this is where we're going to do the swap on the node with 10. And what that's going to look like is we're going to end up switching what the left was pointing to what the right was pointing to, and vice versa. So really, now what our tree is going to look like is 10, 6, and 5. So this is what's going to happen at this point in the tree, or really in this whole tree because it's small. But if you were to extend the same like recursive process throughout a larger tree, you're going to have to do this at every single subtree. So you're just going to have to swap things over in every single subtree. So if we take this example and go a little further, let's make it a little more complicated. So let's do, let's say 10, then 6, and then 7, right? So we're doing post order, so we're going to start at the first leaf from the left. It's pointing to, nulls. I'm going to swap these over. Okay, nothing changes yet. Now we come back up here because we've gone left, we've gone right. And this is where we're going to swap things over. So we're going to have our 10 on our left and our null on our right. So now this is swapped over, but then we got to go on to the next node that we're going to start actually doing stuff on. So remember, we're just going to, let's just say we're going to jump here. So now we're right here. We have null and null, swap them over, right? Jump to the next leaf, null and null, swap them over. So far in this subtree, nothing's changed. But just like in this example, it happens after you come back up from the leaf. So for this node right here, this is where we're going to see the changes. So we're going to see this point here to this 7, and this node point here to this other 6. And then we come back up. We've gone left on 10, right on 10. So now we're going to do a swap on these two. So we're just kind of crossing our cables, right? And what is it going to look like at the very end? We're going to have 10. Then if you just follow the trail, so we're going to have 6. Then we're going to have 7. We're going to have another 6. Then over here, we're going to have a 5. And instead of having the null on our left, it's going to be on our right. And then we're going to have our 10 to the right. So this is what ends up happening at the very end of it. So I hope that made sense. Just at every point, at every subtree, you're just swapping things over. So I'm not going to draw out the tree in the problem, but this is really what's going to end up happening. You can just follow this to get the answer, because yeah, that tree is pretty big, but we can just analyze it. So if we were to start at the very bottom, and if you did this pre-order, it would actually give you the same answer, funny enough. But if we were to start at the very bottom, we notice we had 15 on the right of 6, or on the left. Now it's on the right. We used to have 9 or 72 to the left of 18. Now it's on the right, and we swap the 9 to the left, and so on. The 6 used to be on the left of the 42. Now it's on the right. 18 used to be on the right. Now it's on the left. So that's really what just ends up happening, and that's how you can come up with this answer. I know on the FE though, whenever you see this, it's probably hard to trace out, but yeah, just kind of definitely try it out on a smaller example, because remember, the recursion is going to work the same. Doesn't matter if it's a huge tree like this, if it's a 3-node tree like the one that I showed you guys. So yeah, now we're done with binary trees. We're going to hop into tries. Okay, so we're going to start off, and I'll give you guys 2 minutes to try out this question. Okay, so I'm gonna stop it a little early, but first let's explain what a trie is. So I hadn't done that before, but essentially a trie is, you can think of it as a dictionary. So let's say you have two words you want to add in, right? So you have ABC and let's say A. So a trie, it allows you to have different letters, and really you have an array of pointers, and at every node, each pointer points or kind of it kind of points to what represents a letter. So we have a root node that kind of holds up the entire tree, or sorry, the entire trie, and you have an array of different pointers. Typically, it's 26, which that's the number of letters in the alphabet. You can make a crazy one that's like you can even make it like really as big as you want. I think I did once one. I did one. It was like 50 or something like that once, but so you can make it as big as you want. You're gonna have it as 26 for the foundation exam. So this, since it's the first index, we can think of it as the first letter in the alphabet, which is A. So we might have a node here. If we wanted to represent ABC, we would have this, a pointer to this node, which represents A, because that's index 0, the first letter in the alphabet. And in this node, we have the same thing. And by the way, in every node, you have what's called a flag variable, where it's just a 0 or a 1 that tells you whether or not there's a word there. So we're going to end up having another pointer, right? Another array of pointers, and we're going to have B. So we're going to add in B, 0, another array, right? And when we end up getting to C, it's going to be a little different. So this is going to be representative B at this node, and from here on, we can have what represents C. So this is really the end of ABC, right? So this node signifies the very end. And in this case, you might have other things going out of this node, but let's just say we're inserting for the first time. This C node is where you're going to want to have 1 as your flag variable, because this represents, okay, at this point we have a word. So whatever word we have so far, we have A, then we have B, then we have C. At C, at this point, we have 1 word. So we know ABC is a word in this trie. And same thing if we were to add in hey, right? We would end up having at the pointer representative H, at the pointer representative of E, same thing. And then at the pointer representative of Y, we would have the same thing. Right? But here we would end up having a 1 because this is a word. Meanwhile, even though H and E contribute to a word down the line, it doesn't necessarily represent a word where they currently are at. So that's kind of the idea behind a trie. And there's a whole bunch of different types of problems you can solve with it, but this is what we're gonna, it's just a simple example. So in this case, we don't just have a flag, we have a num words. So let's think about what we might use that for. So num words represents all the words in the sub trie or the subtree of a trie, right? So at A, what might our num words look like? How many words are there somewhere under us and including us? So we have 1 word here. So we're going to have a 1. We're also going to have a 1 here. Let's say we were to have another word. Let's say we had ABA. So we had ABA. And we had a flag variable of 1, right? So this would mean that at B, we have 2. Because even though AB is not a word itself, we have 2 words in our subtree, including, this node that are words. So we have 1 here and 1 here. So in this whole subtree, we have 2, and that'll be reflected on this word, this node right here. We also have 2 here. Since this is the node that holds up the whole tree, this is kind of called like a dummy node. It actually doesn't hold anything, so it would just be 0 and 0. And if we were to apply the same logic of num words, this would be a 1, this would be a 1, and this here would also be a 1, because remember, it's inclusive of itself. So that's kind of what the whole num words variable tells you. So at H, we have 1 word somewhere under us. At A, we have 2 words somewhere under us, same with B, but at A and C here, we only have 1 word, which is itself. So that's the idea behind num words. And what it's saying is, okay, at any given prefix, we want to see, how many words have a certain prefix. So in the case that I'm giving you here, how many words start with a prefix of A and B? So if we look at our try, okay, we go to A, then we end up going to B. How many words have a prefix of AB? So these are words with AB itself, right? So just AB, or anything with that follows AB. It can be whatever length, but anything at all that follows. So we know for sure that there's an ABA and we have an ABC, and we can just have that right here based on this num words variable. So we can see that we have 2 words in the subtree of this prefix AB that tells us, okay, there's 2 things that start with AB, and they can be whatever else, but it starts with AB. So that's what we're looking for. So we have to do this iteratively. So let's just copy this over. That's really what this question is asking. And then it says, you may assume that it's non-null and it has at least 1 lowercase letter in. So we don't have to deal with any weird cases. So first things first, we're going to want to have an index for where we are in the word. So let's just take the length of the word, of the prefix. And we're also going to want to end up making a for loop, so that way we can iterate through the try. So we can just end up, let's just do a for loop actually. So I use X's, I always say that, but I use X's, and then we're gonna want to iterate through the try. So how can we actually go to the next level based on whatever letter it is that we have right now? So the way we can do that is we can end up index based on whatever the letter is from 0 to 25. So we kind of had to adjust it from 0 to 25. And how do we know how to adjust it? It's because it says they're all lowercase letters, right? So we only dealing with lowercase letters. So we can just subtract whatever letter we're at this current index minus lowercase a. Oh, so it looks like someone has a question. Oh, yeah, you can do plus plus or plus plus x or x plus plus. Just in this case, it doesn't matter. But yeah, that's just how I do it. It's actually faster for some reason, like to type out. So that's why I do it. But okay, so first we're going to want to see, is there a node under us that has the next letter? So if we're at A and then we want to go to B, so AB, is there even a B? If there's not a B, we know for sure there's nothing that has this prefix. So we're just going to want to check. So root, and it has children. And this is how we index in. So we take whatever letter we're at right now, minus lowercase a. And that'll give us, okay, based on whatever letter it is, this index in the array. And we can check, okay, if this is null, then we know 100% there's no way that there's going to be anything with that prefix, because there's not a continuation to where we currently are. We can just return 0. And in the other case, let me close this off because the timer is going to go off. So in the other case, if the node is there, meaning it's not null, we can end up going down that path. So we can just do root equals, and we're going to set it equal to the child that we're supposed to go to. Prefix of x minus a. So now we just move down a level, and now we're going to iterate and keep going again. And now we're going to be on the next letter. So in the example that I had mentioned, let's say we had a try where it already has AB. So let's say we have ABA, ABC, and the prefix is AB, right? So we're searching for AB. We're going to be at the primary nodes, so the one that's holding everything up. We're going to say, okay, do we have B? Or sorry, do we have A? We have A. Yes. So now we're going to go down to A. Now from A, we're going to say, okay, do we have B? Yes, we do have B. So now we're going to go down there, but now we're going to hit the end of the for loop, right? So once the for loop is done, we're actually going to be sitting at the very node that we're supposed to say, okay, how many words have this prefix? So what I mean by that is in this example, right? So it actually got kind of messy, but okay. So if we keep this example, we're going to be at index 0 in AB, right? Then we're going to say, okay, do we have A? Yes, we do. So let's move down there. So now we're right here. And here, X is going to be equal to 1. Now we're going to say, okay, do we have the letter at index 1? We have a B. Okay, we have a B. Now let's go down there. So now X is going to equal 2, but we end up hitting the length of this string. So now the for loop is done, right? But remember, we were moving through the try as we were doing this. So now the for loop is done. We've gone through all the letters. So we're actually now sitting at the word itself. So, or the node that's representative of that word. So all we have to do from this point after the for loop, we just return what the number of words is at this point, because this variable tells you the sum of all the words from this node and everything under it. So that's 1 plus 1 plus 0 is 2. So that's kind of how that ends up working out. You just end up landing, if you're not null, then you end up just landing at the variable, at the correct node that represents that prefix. And all you have to do at the end is just return root and num words. That's it. That's all ends up happening with this question. So let's see the answer. Yeah, so we take the length, we do a for loop. If it's null, there's no possible prefix. Otherwise, we end up moving down and we return the root number of words once we end up verifying we can get there and we've ended up landing there. So that is the solution. So we're going to just do one more quickly. And from there, we're going to hop into hash tables real quick. So this one I'm just going to hop straight into because we don't have that much time left. So it says, in many word games, the player is given tiles and you must form a word with those tiles. So given a try that has a dictionary of values and the frequency array storing the information of the tiles a player has, determine the number of unique words you can form with the tiles. Okay. And it says recursing down the try is like placing a tile down, which means updating the frequency array. When you're done trying a tile, you put it back. Okay, so I don't really know what game that is. It's probably like famous, but let's say you have a frequency array, right? And really all a frequency array is just something that allows you to count how many times you've seen any value within a range. So since we're doing lowercase letter, we have from 0 to 25. These are our index. And this, of course, is A, and this, of course, is Z. So let's say we have 3 A's, and then let's say we have a B. Let's say we have 1 B, and then everything else is just 0, right? So this is our frequency array. And let's say we have a try where we have something like this. So we have A, and let's say we have a B, and then we have a B. Right, so this is our try. I know it looks like a binary tree, but it's not. This is a try. And let's say this is a word, this is a word, this is not a word, but this is a word. And actually, let's add on another one. So let's say this one is also a word, and this is A. Okay, so we have this frequency array. So we have 3 A's and we have 1 B. So really what it's saying is, let's use all the tiles that we have. let's try to use all the tiles that we have. And if we have a given letter, okay, let's go down that way. So for example, if we have, let's say we have a Z. So if we have a Z in the try, however, we're not given a tile for Z, we would never end up going to check out anything Z. We might even have ZA something, but we're not going to go down that way because we don't have a Z to use. And in a case where we do have a letter, so let's say we have A, right? So we're going to see, okay, we have an A that we can go to. So let's end up going there. But remember, they say going down to another node in the try represents placing a tile. So if I'm trying to build out a word with a certain number of tiles, I can't reuse the same word somewhere else, right? So what that's going to look like is I'm going to decrement when I end up going to use it. So now at this point, I've only placed down one letter. I've only placed down one A, and I see, okay, I can make a word with this A. So now at this point, the number of words that I can create with these tiles is 1. So let's just say we have answer equals 1, because we can create a word. Here, before we recurse, it's 0. So now we're going to say, okay, let's go through the letters. Do I have an A? I do have an A. So we can end up going down that way. We're going to see, okay, this A is also a word. So we can end up having answer of 1 here. And we're just going to end up, since there's nothing else to go to, let's say we have no children, we can just end up returning this answer variable back up. So now we have answer of 1 from A, and we're going to add that to the previous answer. Now, oh yeah, my bad. I actually, so -1, there we go. So we ended up using 2, so now we only have 1 left. But then now when we end up coming back up, we want to replace it, because now we just used it, but now we want to put it back in the pool, so then we can end up seeing if we can use it somewhere else. So we're going to end up adding it back. So now it's going to look like 2. So now we're back at 2. We're going to go down this way, and we're going to see, okay, do we have a B that we can use? We do have a B. So let's decrement, and let's go down this way. Is this a word? No. So our answer is just going to be 0. But just because this isn't a word doesn't mean we can't make a word further down. So if we notice, we can say, okay, look, we still have 2 A's that we can use. So let's end up going down here. We got to put 1 out of our pool because we're already using it. And we see, okay, this is a word. So now we just have answer of 1. We're going to return this back up. But we're going to put it back in our pool when we're done, because we ended up using it, but there's nothing further to go on. So now we end up putting it back. So now we're back at 2. And notice how this makes sense, because when we came here, we only had 2 A's left. We started off with 3. Then we came here, we only had 1 A left because we used 2. When we came down here, we only have 1 A. We have 2 A's left, but then 0 B's left because we're using it. When we come down here, we only have 1 A left and 0 B's. But then when we end up coming back from this recursive call back up here, we're putting this A back in. So now we're back at, okay, we have 2 A's left over because we started with 3, and we have 0 B's left. So that's really the whole idea behind like how this is working. So we're going to end up returning 1 back up here. So we end up having 1, and now we're done with this recursive call. So we can end up returning 1 up here. So now we have a total of 3. So we had 1 word that we can make right here, 1 word we can make right here, and 1 word we can make right here. So that's 3. And then, yeah, we had to end up replacing these. Now we're back at this point where we're going to end up stopping this recursive call. But before that, we're going to have to like place things back in. So now we're going to have 3. And this is where we're going to go and explore this path here. So notice now we're back at the initial state. So we start off with 3 and 1, and now we're back at 3 and 1 at the root node. Now when we end up using this B goes to 0, and we still have 3 A's. Okay, this answer variable is 1. There's nowhere else to go. let's end up returning 1. Oh yeah, and by the way, we ended up returning 3 from this side. So we ended up being able to make 4 words. So we ended up making, let's see, AA. We can make AA, or actually ABA, and we can just end up making B. So these are the 4 words we can end up making. So I hope that makes sense. We never want to go down a path where we actually can't make the word because we just don't have that. So let's actually get this code and get it done. Okay. So we actually have 2 conditions here. And let's just think about what all these blanks can be. Okay. So what's our res variable? It says that, let's see. So it doesn't tell you that anything's ever going to be null. So we don't even have to handle that. So we don't have to handle like the initial root being null. But at any given point, we're going to want to check, okay, is this a word? The only way you can end up recursing down a path is if you've had the letters to allow you to go down there. For example, if we didn't have a Z, we would never be at a node that has or starts with Z, meaning wherever we start a recursive call, we're going to have that letter no matter where. So we can just take the root flag because we know we're only going down ways that we have enough letters to go down. So root flag, that's going to be a 1 or a 0. In the case of like A or AA, they're just going to say, okay, this is a word, this is a word, this might not be a word. Now we have 2 other cases we have to handle inside the for loop. So when would we want to skip? So the first case that we don't want to skip is if the child is null. So even though the initial case, like the initial root is not known, that's why they don't handle it here. There's a case that somewhere in your subtree, you don't have a node there. And since we don't have any handling for, if null base case, we're going to have to handle it here before we end up, recursing further. So what that's going to look like is if root child or children of I equals null, we don't want to go there. And that's why we're going to continue. We're just going to skip it. Now, there are other cases. Let's think about it. If I have 3 A's and 1 B, why would I ever want to go to a Z or, an X or whatever? Because I don't have those tiles. So we're going to want to handle that other case where we're going to want to skip if the frequency of I, which is the current letter, if it equals 0, then we don't want to go there. So we can just skip that case. So now that we've verified that, it's not null, so we have a node there. And now that we've verified, okay, we have at least 1 letter that we can use. We're going to want to end up taking that letter out of circulation. So before we end up recursing, it's kind of like, okay, I'm placing it down. So out of our 3 A's, once I traverse to A, I'm placing 1 down. So in my frequency array, I'm going to want to decrement it. Now, we're going to want to end up recursing after we ended up actually going down that path. So count words of root. We're just going to go to that child. And frequency is just going to stay the same. Now, when we come back up, remember, once we've ended up using it, we end up coming back up. We want to replace it because now we're going to go on to the next index, meaning the next letter. So we don't want to not replace it because then, we're going to lose that word that we can, or that letter that we can use. So we're just going to want to add it back in, and you can just do that by frequency of I plus plus. So now it's back in circulation. So that's kind of these steps right here where you notice, okay, we're going down. As we go down the try, the frequency is changing down. And then as we go back up, it goes to 2, then 2, and then, so it goes 3, 2, 1, 2, then 1, then 2, then 3. And yeah, then once we're done with going down this way, it ends up coming back up to 1. Because once you end up recursing back to this level and end up returning out, all your letters should still be there. So now if you started with 3, 1, at the very end of this, you should still be left with 3, 1 once you've gone through the whole try that you can explore. So that's the whole idea with this one. Okay, so that is the last try question we're gonna do. Does anyone have any question on that one? If not, we're just gonna hop into the hash table questions. Just do like one or two of those and call it a night. It's almost 9, but I'm gonna, extend it a couple minutes more. Oh, okay. So let's go to hash tables. Okay, this is probably the longest one, so we're not doing this one. Okay, this is an easy one to do. So it says we have a hash function. So we have a table size, and we're given these values right here, return a plus b mod table size. And they give us these values that we're gonna have to insert based on whatever, hashing algorithm they want us to use. So use the following hash function to insert the given elements into the hash table below. Use quadratic probing to resolve any collision. You may assume that the correct table size in this case is always passed to the function with the key being hashed. Okay. So we're given this, and we're going to want to insert it into these locations in the what do you call it? The array. Okay, so first things first, there's two types of probing. There's quadratic and then there's linear. So just real quick, linear, let's do linear. So let's say your hash function is you just take the number and mod it by 10. So this is like really bad. Or actually, let's do it modded by the table size, mod by 4. So let's say you're given 44, a 5, a 6, and then let's say a 1. So if we do 44 mod 4, we're given a 0. So we're going to place 44 in here. We do 5 mod 4, which is the table size. You're going to get a 1. So we're going to place 5 here. If we do 6 mod 4, we're going to end up getting a 2. So we're going to place it at index 2. And the reason I'm placing these right away is because there's nothing there. So whenever there's nothing there, you just, okay, I'm going to place it there and that's it. So index 2, we play, this is actually 6. And right here, we're going to do 1 mod 4. So 1 mod 4 actually ends up coming out to 1. But we notice, okay, we already have something at 1. We have a 5 right here. So what are we supposed to do? With linear probing, you're just going to take, okay, where did I start at? So let's say where we start at. Let's say this function right here. Let's say h of n equals n mod 4. So this is a function we're going to pass in. So whenever we do h of 1, we're going to end up getting a 1, right? So we're going to have this variable. So h of 1 equals 1, right? And this is the starting location. So this is your starting location. What you're going to want to do is just, so you're going to do the starting location plus some sort of number. So let's just say q. Let's say q, right? Q mod and then the table size. So table size, which is 4. And you're going to want to do this. You're going to want to keep incrementing q until you find a free space. So for example, h of 1 we know is equal to 1. Right? So this is what actually let me end up changing this. Okay, so q is going to start off at 0. So q starts off at 0. And we're going to see, okay, so we end up passing this in, we end up getting this number, and we're going to see, okay, can we end up placing something here? No, there's something there. So now we're just going to want to increment q. And I think that formula that I wrote was wrong. I'm going to go back to it, but you're going to end up going to the next value and seeing, okay, can I place something here? No, I can't. We're going to end up going to the next value and placing it here because we found something empty. Now, let's say we had something here. Let's say we had a 10 here. What's going to end up happening is we're going to end up seeing, okay, now we can't place anything here. We're currently at index 3. So if we keep on doing the same thing that I had mentioned, 3 plus 1, and then we do mod by the table size, which is 4, then now what's going to end up happening is we're going to go out of bounds if we don't mod. So if we don't mod, we're going to have 4, and index 4 is out of bounds. So we're going to want to wrap back around this location. So we do mod 4, and that's going to give us index 0. And of course, we're going to see, there's no space, so we're just going to keep going forever. But that's just an example of how the mod works. And this formula, let me actually fix it, because so let's just say, so h of n, so we take our starting location plus q mod the table size. So this is what I meant to do, where q starts at 0 and it just increments up. So we take the starting location. If it starts at 0, so 1 plus 0, it's still taken. 1 plus 1, still taken. And we're also modding this by 4. Right, and then 2 plus 1 mod 4 is taken. Then we try out 3 plus 1 mod 4, it's still taken, and so on until we find an empty spot. Now with quadratic probing, let me actually let me just write down these numbers. So with quadratic probing, the way it works is okay, so let's say I do the same thing. So now we're going to do mod 5. So this is what our function is going to be. H of n equals n mod 5. So I'm just going to add in 0. Let's add in 5, and let's add in 6. So 0 mod 5, we're going to end up placing it here because it's divisible by 5. 5 mod 5 is just going to end up going to 0, right? So 5 mod 5 is 0, but there's something here. So what's going to end up happening is we're going to have another factor, but we're going to have a factor like q, but in this case, it's going to look like this. So we're going to have a function where taking h of n plus q squared, and we're going to mod this by the table size. So this is how it's working. So we have our starting location. So h of n, this right here, ended up giving us 0. So now we're going to do, so we have 0 plus 0 squared. That just tells us 0. Okay, there's something there. Now we're going to keep going, incrementing q, right? We're going to increment q. So now it's going to be h of n, which was started off at 0, plus 1 squared. So now we're at 1. Okay, 1 is free. So let's place it here. So now we're going to place 5 here. Then 6 is mod 5. It's going to end up giving us a 1. And we know that at index 1, there's something there. So we're just going to follow the same process. We're only going to bump up by 1. And now we're going to place it here, because we end up having 1 plus 1 squared. So we're going to place 6 here. Now, let's say we try to put in 10. So 10 mod 5 is 0. So now we're going to start off here again. So we know that at this point, we're going to have 0 plus 0 squared equals 0. It's taken. Now we're going to make q equal to 1. So 0 plus 1 squared equals 1. We know that 1 is taken. So now what we're going to do is take the starting location. So 0 plus 2 squared. And yeah, we're also modding this, right? So we're also modding this. I forgot to mention that. But now we're going to mod this by the table size, which is 5. So now we have 4 mod 5, which is just 4. And that's where we're going to end up placing it. So over here. So it's going to be where we're going to place 10. So this is the whole idea behind how quadratic works. So we ended up starting here. Then we ended up jumping over here. Now we're going to make another jump. That's actually so 1, 2, 3, 4 away from this initial location. And let's say we're gonna go again. If this was taken, then now we would do q equals 3, and now we'd have 3 squared, so now plus 9. So 0 plus 9 mod 5, we would have index 4, and then we would keep going and so on. So that's the way that that works. So it's actually not that bad. It's pretty simple. And I think if you guys just write these down or remember these, it'll be a lot easier to kind of think about it. But overall, it's not a hard thing to get down. Okay, there we go. Back again. Okay, I actually don't think I'm gonna have enough time for this one, but let's just write it down. Okay. So I'm just gonna do it like this. So I don't have to draw this out. Okay, so we're given these values, and what we're gonna start off with is the key and then the table size. So we know the table size is 10, and so A equals key mod 100. So if we start off with 255, that's gonna be mod 100. We're gonna end up with 55, and then we're gonna divide this by 10, right? So we're starting off with this number. So this is gonna give us 5. Now here, we're gonna have key mod 10, and that just gives us the last value, or the last number. So we're gonna have a 5. So this is gonna give us 5 plus 5, 5 plus 5 mod 10, which is just 0, because 10 mod 10 is 0. So right here, we're gonna place 255. Okay, now let's reset. And we're gonna go to this number. So this number mod 100 is gonna be 23. Now we're gonna divide that by 10, and that gives us a 2. Now we're gonna take the key, get the least significant digit, so that's gonna give us a 3. So we get a 3. Now we're gonna do 2 plus 3. 2 plus 3 mod 10. So it's going to be at index 5. So at index 5, we're going to end up placing 151, 5, 2, 3, 1523. Okay, now let's go on to the next number. So we're going to end up with a 93 divided by 10, give us a 9. And then now we're going to end up getting P mod 10. So we're going to end up getting a 3. Now we're going to have 9 plus 3 mod 10, which gives us 2, because 12 mod 10 is 2. So 5893. Now we have 800. So 800 mod 100 is just going to give us 0. 0 divided by 10 is going to give us 0. Now we're going to do key mod 10 is going to give us 0 again. And now we're going to have 0 plus 0 mod 10. And this is going to give us another 0. So now here's where we're going to see, okay, we have something at 0. So what are we going to do? We're going to use the same formula. So we can use, think of it like this, hash of 800, and then we pass in our table size, right? So 10 plus q times q, all modded by the table size. Right, so let's say our q is 0. We know that hash of 800 and then right 10, that's going to be equal to 0, because we ended up getting that right here. So we're going to end up with a 0. Q is going to start at 0, so 0 squared is 0. Okay, there's something already there. So now let's bump this value up to 1. So now we're going to have 1 0 plus 1 times 1. So there's going to be 1 mod 10 is still 1. So now we're going to place it here. So that's where we have 800. And now we're going to go to 256 or 256, 956. It's been a long session. Okay, so now 956. All right, so what's this going to end up giving us? So we're going to have, so 956. If we mod it by 100, we get 56. Divide that by 10, we get 5. Then we mod the whole thing by 10, we get a 6, so the last digit. And now we're going to do 5 plus 6 mod 10. Yeah, mod 10. And then this is going to end up giving us a 1 because 11 mod 10 is 1. So let's see. So 1 plus, and remember we start at 0 times 0. So there's something right here, right? So there's something there. So now we're going to bump it up to 1. Okay, so at index 2, is there something also? Yes, there is. So now we're going to, instead of 1, now we're going to bump this up to 2. So now let's check this out. So now we have 2 times 2 plus 1, that's 5. Mod 10 is still 5. Okay, we still have something at 5. So now let's bump Q up. So bump it up to 3. Here we're going to end up doing 3 times 3, which is 9 plus 1, mod 10 is going to give us 0. So now we're going to do this again. Bump it up to 4. Now we have 16 plus 1, 17, mod 10. That's going to give us an index of 7. So now we're going to place 956 here. And this should be the final answer. So yeah, just keeping track of it like this is pretty easy. You know, you can just, this answer, this number is always going to stay the same. The only thing that changes is your Q. And another trick that I would say is, if you know that there's something somewhere, so let's say, okay, 256 already placed. There's no reason for me to try to recalculate, okay, where should I go next? Like in my head or doing the math. You're like, okay, you can just end up kind of looking at it and seeing, okay, I can skip doing this multiple times. So for example, if this something's already here, and we know something's already here, and how can I explain what I'm trying to say? Like, you can kind of see, okay, where have I gone from this point on? So you can see, okay, this is the next possible place I can place it on based on things you've already calculated before. So you know for sure it's not going to be here, so you can just skip to 2. Okay, you can check here, you know for sure it's not going to be at 2, so now let's keep going to 3, 4. So there's some cases where you can just kind of skip over some values and know which is the next one you have to try. So if for index 0, you've already tried 0, 1, 2, 3, you know the next one is going to have to be 4. You don't have to recalculate 0, 1, 2, and 3 based on whatever this hash value is. So this is really the key to it. If you've already calculated like hash that returns 1 before, you don't have to do it again. Skip to what you remember it was. So if you ended up at 3, go to 4, and then 5. If you end up with hash of 1 again, don't start at 1, 2, 3, or 4, or 5. Just go to 6, because you know you've already calculated that. You don't have to keep doing it. So yeah, that's the whole idea behind this. So let's see. Did we end up getting it? Yeah. So 5 and then 6. So that's about it. And they actually show you where you had some collisions. So there was a collision from here, we placed here, and then here, we collided here, then here, then I think back here, and then we ended up placing here. So yeah, that's pretty much it. We're not gonna do another question. It'll probably be easy, but yeah, I'm just gonna call it there because we were supposed to end at 9:15. So that's it for this session. Does anyone have any last minute questions? Yeah, no problem, for sure. Okay, so no questions. All right then. Well, I hope you guys have a good night, and Yeah, I'll see you guys next week. Peace.